Hey, today I wanted to talk about radioactivity and specifically fission. And there's two main types of reactions that I want to talk about. These are nuclear equations, and when you look in terms of the format of nuclear equations, you have the symbol given in the center here. So in this case, radon. To the upper left of that is the mass of that particle or that isotope. And the lower left is the number. So 86 is the number for radon. Now, one type of radioactive decay is alpha decay. And in alpha decay, basically you start out with a nucleus and then it splits into pieces. Specifically, a helium atom or alpha particle leaves, and then the residual remainder of the nucleus is there as well. So you'll notice when this happens, you have radon here with a mass of 222. Helium has a mass of 4, so the remaining mass of the other particle is 218. There's 2 protons in helium, so the atomic number goes from 86 down to 84, which then makes the radon into polonium. This would be another example of that with plutonium with a mass of 240, number 94, having an alpha particle or helium atom leave it, which again has a mass of 4 and 2 for the number of protons or the atomic number. And that will again lower the mass by 4 to uranium-236 and then 92, which is the atomic number for uranium. A second type of chemical, or not chemical, but nuclear reaction is beta decay. And in beta decay, essentially what happens is an electron is emitted from the nucleus, and specifically, you have a neutron emit a electron or beta particle. There's also an antineutrino gets emitted, leaving then a proton. So because of that, you have a neutron converts to a proton and an electron, which means that the number actually increases by 1. So here we have radium-228. The mass stays essentially the same, 228. But the number, since a neutron converts into a proton, the number goes from 88 up to 89. So we've gained 1 proton, we've lost 1 neutron. Okay, you also get the beta particle or electron is emitted, again, with virtually no mass and a -1 charge. Another example, really common, is carbon-14. Carbon-14 has 6 protons. When you have beta decay, one of the neutrons in carbon-14, again, emits the electron or beta particle, and the proton is formed, meaning that instead of having 6 protons, you have 7 protons. The mass, though, stays at 14 because all that happened was the neutron converted into a proton with the emission of a beta particle, or again, a beta particle is essentially an electron. Now, this happens at a regular known rate for different elements. And half-life is when half of the original element that was there has decayed, or the isotope that was there has decayed into its daughter product. So after 1 half-life, half of the stuff remains. 2 half-lives, a quarter of it does. 3 half-lives, an eighth of it does, etc. And you can graph this out for something like carbon-14, where carbon-14's half-life is about 5,720 or so years, or 730 years. So by knowing that, you can then look at a sample like a tissue or something, or a tree sample, or anything from a living organism, and look at the amount of carbon-14 in it. And if half is there, it means it was about 5,700 years old. If a quarter is there, it would be twice that, or somewhere a little over 11,000 years old. So you can use the amount of carbon-14 remaining in a sample to tell how old it is, up to about 50,000 years. At 50,000 years, there gets to be so little that in there that you can't tell how much is there. So this was just, I wanted to go over alpha decay, beta decay, and the concept of half-life.